Welcome to Altair Engineering Training and Support. I am Apur Bapat. Welcome you all in BAJA Student India online training session. The agenda of this training series is on day one. I am going to show you how to perform 1D geometry editing and meshing along with the theory of FE and CAE. We'll see how to create a load cases for static analysis, front impact, rear side, torsional bump, uh, and on day 2 we will see the 2D side of the roll cage where I'll show you the 2D geometry editing meshing and the same static analysis on 2D meshed roll cage. Then on day 3 we will see how to perform the dynamic crash analysis for front impact, side impact, rear and impact. And on day 4 we will see some 3D geometry editing and meshing using knuckle and hub. So we'll start with the theory of FEM and CAE. So the first question is, why do we carry out meshing and what is FEM? So the basic idea of FEA is to make calculation at only limited number of points and then interpolate the results for entire domain, surface or volume. Any continuous object has infinite degrees of freedom and it's just not possible to solve the problem in this format. So finite element method reduces the degrees of freedom from infinite to finite with the help of discretization or meshing, that is nodes and elements. FEM, and it is a numerical method. It's mathematical representation of actual problem, and FEM is an approximate method. The finite element method only makes calculation at limited number of nodes and then interpolate the results for entire domain, surface or volume. As you can see here, we now define what is FEM. So it consists of finite element method. Finite means any continuous object has infinite degrees of freedom and it is not possible to solve the problem in this format. The finite element method reduces the degrees of freedom from infinite to finite with the help of discretization or meshing. Element, all the calculations are made at limited number of points known as nodes. The entity joining nodes and forming a specific shape such as quadrilateral or triangular is known as element. To get a value of variable, say displacement, anywhere in between the calculation points, an interpolation function as per the shape of the element is used. Method. There are three methods to solve any engineering problem. Finite element analysis belongs to numerical category method. How the results are interpolated from a few calculation points. It is okay that FEA makes calculation at limited number of points, but the question is how it calculates value of unknown somewhere in between the calculation points. This is achieved by interpolation. Consider a four-noded quadrilateral element. Uh, a four A quad 4 element uses the following interpolation formula. FEA calculates the value at outer nodes 1, 2, 3, 4, that is A0, A1, A2, A3 are known. The value of variable anywhere in between could easily be determined by just specifying x and y coordinate in the above equation. For 8 noded quadrilateral, the following parabolic interpolation function is used. Now we will see what is degrees of freedom, DOF. In the example, an object is fixed at one end and a force is applied at point P. Due to the force, the object deforms and the point P gets shifted to new position P dash. When can we say that we know the solution of the above problem? If and only if we are able to define the deformed position of each and every particle completely. So now we define how to define the DOF, that is degrees of freedom. The minimum number of parameters, that is motion, coordinate, temperature, required to define the position of any entity completely in space is known as degrees of freedom. Consider the following 2D planar problem. Suppose the origin is at the bottom left corner and is known. To define the position of point A completely with respect to origin, we need two parameters, that is x1 and y1, and in other words 2 DOF, translation x and y. Consider that the point A is a part of line. Now one angle should also be defined in addition to two translation, that is 3 degrees of freedom. Suppose point A and B are shifted out of plane and the line is rotated arbitrarily with respect to all the three axes. The minimum number of parameters to define the position of point A completely would be 6 degrees of freedom, that is 3 translation and 3 rotation. DOF is very important concept. In FEA, we uses it for individual calculation points. The total DOF for a given mesh model is equal to the number of nodes multiplied by number of degrees of freedom per node. All the elements do not always have 6 degrees of freedom per node. The number of degrees of freedom depend on the type of element, 1D, 2D, 3D, the family of element, thin shell, plane stress, plane strain membrane, and the type of analysis. For example, a structural analysis a thin shell element has 6 degrees of freedom per node, that is displacement unknown, 3 translation and 3 rotation, while the same element when used for thermal analysis has single DOF, that is temperature unknown. For a new user it is a bit confusing, but there is a lot of logic, engineering and mathematical thinking behind assigning the specific number of degrees of freedom to different element types and family. Now we will see different element types. So 1D element is used when one of the dimension is very large in compared to other two. The element shape of 1D element is line. Additional data from the user required to define the 1D element is remaining two dimension, that is area of cross section. The element types available in 1D is rod, bar, beam, pipe, axisymmetric shell, etc. Practical application where 1D elements are used is long shaft, beam, pin, joints, connection elements, etc. 2D elements. It is used when two of the dimensions are very large and compared to the third one. Element shape is chord or tria. Additional data from the user is remaining dimension, that is the thickness. Element type is thin shell, plate, membrane, plane stress, plane strain, axisymmetric solid, etc. Practical application is sheet metal parts, plastic components like instrument panels, etc. 3D elements are used when all the dimensions are comparable. Element shape is tetra, hexa, penta, pyramid. Additional data from the user is nothing. Element type is solid. Practical application is transmission casing, engine block, crankshaft, etc. There are some other types of elements also used in CAE. Then we will see when to use 1D element. When one of the dimension is very large in compared to the other two, element shape is line. Additional data from the user is remaining two dimension, that is the cross-sectional area. Element type is rod, bar, beam, pipe, axisymmetric shell, etc. Practical application is long shaft, beam, pin joints, connection elements. So there are different types of 1D elements, and when to use which type of 1D element we can see here. Like rod elements we use for tension and compression. Rod element supports only 2 degrees of freedom, that is translation along an axis and rotation about that axis. Bar element supports 6 degrees of freedom, that is 3 translation and 3 rotation, but it is only applicable for symmetric cross sections. Beam element supports all the 6 degrees of freedom and for unsymmetric cross sections also. When to use 2D elements? 2D elements are used when two of the dimensions are very large in compared to the third one. Element shape is chord, tria. Additional data from the user is remaining dimension, that is the thickness. Element type is thin shell, plate, membrane, plane stress, plane strain, axisymmetric solid, etc. Practical application is sheet metal parts, plastic components like instrument panels. Why is 2D meshing is carried out on mid surface? Quite often the geometry of thin walled 3D structures as shown in the image below is simplified to a geometric model with low dimensionality. This is typically called a mid surface model. The mid-surface model is then meshed with a 2D element, thus there is no need of detailed volume mesh as the thickness of the geometry is virtually assigned to 2D elements. Mathematically, the element thickness specified by the user is assigned with half in Z plus and half in Z negative direction. Different types of 2D elements are tria and chord. We have a first order tria and second order tria. 3D elements are used when all the three dimensions are comparable. The element shapes available are tetra, penta, hexa, pyramid. Additional data from the user is nothing. Element type is solid. Practical application is gearbox, engine block, crankshaft. The different types of 3D elements used is first order tetra, second order tetra, first order penta, second order penta, first order brick or hexa element, second order brick or hexa element, first order pyramid, second order pyramid. Now we will see how to do 1D meshing on roll cage structure. So once you start the Hypermesh, you can go to start all programs, alter Hypermesh and click on Hypermesh if you are using full version of Hypermesh. If you are using the student edition, click on HyperWorks. Once you click there, you will see this window will pop up. So you have to select a user profile as OptiStruct if you are using version 12 and 13. If you are using version 11, HyperWorks version 11, then you have to select radius bulk data. Click OK to load the user profile. Open the file of your roll cage. Now I will start creating the solver deck. So the first step to create the solver deck is create material. So I will enter the material name as steel, define a type, select a type as isotropic, card image as mat1, click on create edit, enter the values of e new row. By default the software takes the values of mild steel. You can change these values by entering the different values here. Click return, again click return. On the model browser you can see my material has been defined. Now I will define the cross section. So to define a cross section I will go to 1D page. On 1D page I will click on hyperbeam. Select the standard section radio button. Standard section type library as hyperbeams and standard section type as thin walled tube, and click on create. Let's assume I have entered the outer diameter 20 and inner diameter as 18. So I am considering my pipe thickness to be 2 mm. So I'll click on model view to go back to Hypermesh and click return. You can see on the model browser my cross section has been defined. Now I will create the property. So to create the property I will click on the property collector icon, which is in right hand side of the material icon. So I will enter the property name as roll cage property, define a color to it, select the type as 1D, card image as P-beam, material as steel, beam section as tube section, and click on create edit. So you can see it has taken the values of A, IXX, IYY and J, which is required to define the cross section. Now I will go to component collector icon, select the radio button as update, click on comps, select the component which is available here, click select, turn off the radio button from no property to property, click on property, select the property which I have already created and click on update. So now my component has been updated with proper property. Now before going further, I will quickly check whether all my lines are properly connected or not. So I will just click on these lines, and if there are any duplicate, then also I will try to find it out. So the start point and end point of these lines have to be proper. If it's not proper, then we will join them properly. So I'm just checking here whether all my lines are properly connected or not. So as you can see, all the lines in my geometry is properly connected. So now I'll go for meshing. So to do the meshing, 1D meshing, I'll go to 1D page. On 1D page, I will click on line mesh panel. Select all the lines. Select the element configuration as bar 2. Select the property which I have created earlier. Enter the element size, say 20, and click on mesh. Then I will click on return. Again click on return. So I will turn off the geometry. So this is the 1D meshing is done. So now I will turn this on to see whether all my pipes are able to view, I am able to view in a 3D or not. So I am able to view all these pipes on 3D element representations. I will again turn it off. Now I will create the load collectors. I will start with front impact force. Define a color to it, say create. Then front impact constraint. Define a separate color to it. Similarly, side impact force. Define a color to it. Side impact constraint. Rear impact force. Create. Define a color to it, say create. Then torsional force. Create. Torsional constraint. Constraints means reaction force. And bump force. And bump constraint. Now we'll apply these forces. I'll go in analysis page forces. Make the front impact as the current one. Select these nodes, which is in the front impact side. Click on save to know how many nodes are there. So there are total 26 nodes. So let's assume I am applying a force of 12,000 divided by 26. So this is the force I want to apply. So the direction is in z-axis and say create. So you can see my force has been created. Now I'll make the front impact constraint as current. Go to analysis constraint. Select the suspension mounting points. I'll turn off this. Make the SPC as current. Side impact force as current. Select the analysis force panel. Click on nodes. Save. We have 54 nodes. So let's assume 12,000 divided by 54. This time the direction is x-axis. So I will select x-axis and say create. So my force has been created. Now I will create constraint. So make the constraint as current. Go to analysis constraint. Select the suspension mounting points. And say create. Then I will turn off this. Make the rear one as the current, or you can first make this the constraint for rear and then apply the forces. Similarly here also. Say create. Then I will make the forces. Why I have done this? Because sometimes some student ask me that why you are always creating the forces first. So you can create the constraint first also. That doesn't matter. So I have 33 nodes. So 12,000 divided by 33 in negative z direction. Create. Then torsional force. select the suspension mounting points, say 2500 in y-axis, create. Similarly here also minus 2500 in y direction, create. Then torsional constraint, make this as current. Analysis constraint, make the suspension mounting points. Then bump force as create and make the bump constraints. Now I will define the load steps. So I will start with front impact, SPC, force, create. You can see on the model browser my front impact is being created. Side impact, force, SPC, create. Rear impact, constraint, force, create. Torsional, constraint, force, create. Bump, constraint, force, create. So now my solver deck is complete. So I will save this file. Go to analysis, OptiStruct, export option to all, run option to analysis, keep the memory as default and click on OptiStruct. So my analysis has been completed. If you get any error, feel free to take the screenshot of this error and send us to us along with the HM file. So the displacement value for front impact is coming as this much. For side impact, rear impact, torsional, bump. And the stresses values for front, side, rear, torsional, bump. And you can also see the animation. So front, side, rear, torsional, bump. So in this way I have ended with this session. Thank you very much for attending this session. If you have any queries, feel free to ask us at edu-support@india.altair.com or you can contact me also. Thank you very much.